Tonight, we are going to talk about objects so extreme that they do not simply pull matter through space. They change what space means. A black hole is not just a dark sphere floating in the universe. It is a region where gravity becomes so strong that light itself cannot escape, where time can slow near the edge, where falling gas can glow brighter than entire galaxies, and where the laws of physics begin to point toward questions we still cannot fully answer. The strange part is that black holes are not science fiction anymore. We have tracked stars orbiting the invisible monster at the center of the Milky Way. We have seen the shadow of a black hole. We have detected gravitational waves from black holes merging across deep space. And yet, the closer we look, the more they force us to ask whether our understanding of reality is complete. Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the universe. And write in the comments where you are watching from and what time it is where you are right now. It is strange to think that people are listening from different parts of one small planet, while somewhere far away, black holes are bending time itself. Tonight, you are watching the Just About Space channel, talking about why black holes break our understanding of reality. The first thing to remove is the picture most people carry in their head. A black hole is not a dark planet. It is not a solid sphere. It is not a mouth in space waiting to swallow the universe. That image is useful for fear, but not for understanding. It makes a black hole feel like an object with a surface, an edge, and a body you could point to in the same way you point to a star or a planet. But the closer we get to the real physics, the less that picture works. A black hole is better understood as a region of space-time. That sounds abstract, but it is the only way to avoid the wrong image. A planet is an object inside space. A star is an object inside space. A black hole is different because the shape of space and time around it is part of the object itself. You do not understand it by imagining a surface. You understand it by asking what paths are still possible. A region where gravity has become so intense that there is a boundary beyond which light can no longer escape to the outside universe. That boundary is called the event horizon. It is not a wall, a shell, or a surface like the ground under your feet. It is a point of no return, written into the geometry of space and time. A star can shine, a planet can reflect, a nebula can glow. But inside the event horizon, light itself loses the ability to reach the rest of the universe. The most ordinary messenger in astronomy, the thing we use to see almost everything, becomes trapped. This is why black holes are black, not because they are painted dark, not because they absorb light like black cloth, but because beyond a certain boundary, every path light could take points inward. Escape is no longer part of the future. At the event horizon, the escape speed reaches the speed of light. Since nothing carrying information can move faster than light, nothing from inside can return to the outside. Not dust, not gas, not a signal, not a final flash from something falling in. The boundary does not need to grab you. It only needs to make every possible outward path impossible. That is the first reason black holes disturb our understanding of reality. They are not dangerous because they chase everything. They are dangerous because they change what direction means. Outside the event horizon, a black hole still has gravity like any other mass. This is important because black holes are often imagined as cosmic vacuum cleaners, sucking up everything nearby simply because they exist. That is not how they work. A black hole does not reach across the galaxy and pull every star into itself. It does not magically increase its gravity just because it is dark. Gravity depends on mass and distance. If the sun could somehow be replaced by a black hole with exactly the same mass, Earth would not instantly spiral inward and disappear. Earth's orbit would remain broadly similar because the gravitational pull at Earth's distance would be set by the same mass. The real disaster would be the loss of sunlight. Earth would freeze, not because the new black hole would suck it in, but because the sun's heat and light would be gone. At a safe distance, you can orbit a black hole. Stars orbit the supermassive black hole at the center of the Milky Way. Gas can orbit before falling inward. In some systems, black holes have companion stars, and material pulled from the companion forms a hot disk around the black hole. The danger grows when matter gets too close, not because the black hole has supernatural hunger, but because gravity, speed, heat, and tidal forces become extreme. This is where the word hole causes trouble. A hole, in everyday life, is an absence, a gap, a missing piece, a place where something used to be. But a black hole is not empty nothingness. It is tied to an enormous concentration of mass. It may form when a massive star collapses after exhausting the fuel that once held it up against gravity. It may grow by merging with other black holes or by feeding on gas. Supermassive black holes can sit at the centers of galaxies with masses millions or billions of times that of the Sun. The hole is not a lack of something. It is the consequence of too much gravity in too small a region. That is why the name is both perfect and misleading. Perfect, because no light escapes and the region appears black. Misleading, because it suggests an opening into a simple emptiness, when the real idea is a boundary around collapsed mass and curved space-time. That is very different from seeing a planet. When a spacecraft images Mars, it photographs a surface. When a telescope observes Jupiter, it sees cloud tops. With a black hole, the object is not visible in the same way. The information comes from orbits, radiation from nearby matter, gravitational lensing, X-rays, radio waves, and gravitational waves. A black hole is recognized through effects. Stars moving around something invisible, gas heating as it spirals inward, light bending around a region it cannot cross back from, space itself ringing after two black holes merge. This makes black holes feel almost unreal, but they are not imaginary. We have strong evidence for stellar mass black holes in binary systems. We have watched stars orbit Sagittarius A, the supermassive black hole at the center of the Milky Way. We have imaged black hole shadows and detected gravitational waves from black hole mergers. The problem is not whether black holes are real. The problem is that their reality is hard to fit into ordinary human thought. Human intuition evolved in weak gravity. We understand falling because we fall a short distance to the ground. We understand light because it reaches our eyes. We understand time because clocks around us agree well enough for life. We understand objects because they have surfaces, edges, and locations. Black holes live outside that comfort zone. They force us to think about regions where a boundary is not a surface, where darkness is not emptiness, where gravity is not just a pull, where time can disagree between observers, and where the future itself seems to narrow. That is why the simplest question becomes difficult. What is a black hole? If we answer a dead star, we are only partly right. Some black holes form from collapsed stars, but supermassive black holes are far larger and have more complex growth histories. If we answer a hole in space, we create the wrong picture. If we answer a place where nothing escapes, we are closer, but still not finished. The event horizon tells us about escape, not about every detail of what the black hole is. The deeper answer involves space-time. But before we go there, it helps to stay with the boundary. The event horizon is the line that separates the universe that can still communicate with us from the region that cannot. Outside it, events can send signals outward. Inside it, events are cut off from the outside universe. If something crosses that boundary, the rest of the universe can no longer receive a normal message from it. That is why the name matters. Event horizon. Not object horizon, not matter horizon, event. It marks the limit beyond which events can no longer affect distant observers by sending light or information back out. Something can happen inside, but outside observers cannot receive the news in the ordinary way. This is where black holes begin to feel existential. They do not merely hide objects, they hide events. They create regions of the universe from which the story cannot be reported back to the rest of space. And yet, from the outside, the black hole still has measurable properties: mass, spin, electric charge. Though astrophysical black holes are expected to be nearly neutral, a black hole can be described in surprisingly few external parameters. This idea is often summarized by the phrase that black holes have no hair, meaning that many details of the matter that formed them disappear from the outside description. That is another uncomfortable thought. The universe can erase detail from view: a library, a spacecraft, a cloud of gas, a star, a planet, all reduced from the outside to mass, spin, and charge once hidden behind a horizon. The original complexity does not remain available to distant observers in any simple way. Still, the black hole does not need drama to be extreme. It does not need to roar. It does not need to burn. A black hole can be silent and invisible, and still be one of the most powerful structures in the universe. If no gas surrounds it, if no stars pass nearby, if no merger is happening, it can be almost impossible to notice. It can drift through space with only gravity revealing it. The quietness is part of the strangeness. The most extreme object may look like nothing at all. This is why the phrase black hole can be too small for what it describes. It sounds like an object. It is also a rule about motion, light, the future, and which events remain part of the outside universe. The event horizon is not built from material. It is built from impossibility. Cross it, and escape stops being an option allowed by space-time. That is why the first chapter of the story must remove the cartoon. Black holes are not space drains. They are not hungry mouths. They are not magical portals in the normal scientific picture. They are what happens when mass and gravity push space-time into a form so extreme that the outside universe loses access to what falls too far in. And once that picture is in place, the next question becomes unavoidable. How can gravity do that? How can something we experience as a pull toward the ground become a boundary that traps light? How can a region of space become a place where every possible future points inward? How can the shape of the universe decide what can and cannot escape? To answer that, we have to leave the old idea of gravity behind. The next step is not to think of gravity as a force pulling objects through space. It is to think of gravity as the shape of space-time itself. The next step is not to think of gravity as a force pulling objects through space. It is to think of gravity as the shape of space-time itself. Einstein's general relativity changed the question. Gravity was no longer only a force acting inside space. Space and time became active parts of the story. Matter and energy shape space-time, and curved space-time tells matter and light how to move. This is the idea that makes black holes possible. In the modern sense, the difficult part is that curved space-time is not something we can see directly. We see its effects. A planet follows a curved path around the sun. Light from a distant star bends when it passes near a massive object. A clock lower in a gravitational field ticks at a slightly different rate from a clock higher up. None of these effects require gravity to be imagined as a hand pulling through empty space. They can be understood as motion through a space-time that is no longer flat. In weak gravity, the difference is subtle. Around Earth, the curvature is gentle enough that the old language of force still feels natural. Around a black hole, the curvature becomes the main story. The closer something comes, the less useful the old image becomes, because the possible paths through space-time are being reshaped more violently. A straight line is no longer simple. Light normally seems to define straightness. In empty space, a beam travels forward, and we trust it to show us where something is. Near a black hole, even light follows curved paths. Some light can swing around the black hole before escaping. Some can orbit briefly in unstable paths. Some crosses the horizon and never returns. The black hole does not need to touch the light. The geometry tells the light how to move. The event horizon is not a material object placed in space. It is a boundary created by the way space-time is curved. Outside it, there are still paths that lead outward. Inside it, every possible future path leads deeper inward. Space and time are tied together, and the geometry decides what future paths exist. Crossing the event horizon does not mean hitting a physical surface. It means entering a region where the direction we would call outward no longer leads to escape. Even light, moving at the maximum speed allowed by physics, cannot choose a path that returns to the outside universe. The black hole does not need to pull faster. The geometry has changed. One useful way to feel this is to imagine rivers, though every analogy is imperfect. Far from a waterfall, a boat can move upstream if its engine is strong enough. Closer to the waterfall, the current becomes faster. At some point, the current flows inward faster than the boat can move outward. The boat might still point upstream, but every possible motion carries it toward the falls. This is why the event horizon is not a place where the black hole suddenly becomes strong in the ordinary sense. It is the place where escape stops being one of the available futures. Outside the horizon, a powerful rocket could still, in principle, fire outward and escape if it had enough energy. At the horizon and inside it, that idea loses meaning. The issue is no longer fuel. It is the structure of space-time. The same black hole can therefore be harmless from far away and impossible to escape from nearby. That is not a contradiction. It is what gravity always does, pushed to an extreme. Distance matters. A black hole with the mass of a star does not pull on a distant planet more strongly than that same star did. But if matter gets compressed into a small enough region, there can be a zone close to it where no outward path remains. That zone has a size. For a non-rotating black hole, the size of the event horizon is connected to what is called the Schwarzschild radius. The formula is not needed to feel the idea. More mass means a larger horizon. Compress Earth into a black hole, and its horizon would be tiny compared with the planet we know. Compress the Sun into a black hole, and the horizon would be only a few kilometers wide. Compress millions or billions of suns, and the horizon can become larger than the orbits of planets. Mass decides the scale of the boundary. Geometry decides the meaning of the boundary. This is why light cannot escape. Not because light gets tired, not because the black hole blocks it like a lid. Because inside the horizon, the future direction available to light points toward the center, just as surely as tomorrow points after today. That is the most disturbing part of black hole geometry. The center is not merely a place in space. For something inside the horizon, moving inward becomes tied to moving forward in time. Avoiding the center becomes less like avoiding a location and more like avoiding next Tuesday. It is not a direction you can simply turn away from. Light bends. Clocks disagree. Orbits precess. Gas heats and spirals. Stars whip around invisible mass. The path of the future itself narrows. General relativity has passed many tests, and black holes are among its most powerful predictions. When massive stars collapse, when dense objects merge, when light travels near strong gravity, Einstein's theory gives a language for what happens. It does not describe gravity as a simple pull reaching through empty space. It describes the stage itself becoming curved. This is also why black holes can be different sizes even when the idea is the same. A stellar mass black hole may have a horizon only tens of kilometers across. A supermassive black hole at the center of a galaxy can have a horizon wider than an entire planetary system. The boundary grows with mass. The concept is the same, but the scale changes enormously. That difference between perspectives is one of the reasons black holes are so unsettling. A black hole does not give everyone the same story. A distant observer, watching something fall toward the horizon, sees the light from that object become increasingly redshifted and delayed. The falling object appears to slow, fade, and approach the horizon in a way that becomes stretched from the outside point of view. But from the falling object's own perspective, crossing the horizon can happen in finite time. Two observers can describe the same event in radically different ways, and both descriptions have meaning within relativity. In ordinary life, people can disagree about what happened, but they do not usually disagree about whether a clock is running at the same rate in a physically measurable way. Around black holes, time is no longer a universal background shared equally by everyone. Gravity affects time. Motion affects time. Position in a gravitational field affects time. Time becomes local. This does not only happen near black holes, it happens near Earth too, but weakly. Clocks at different altitudes tick at slightly different rates, and satellites must account for relativity. Black holes simply take the same principle and push it into a domain where it becomes impossible to ignore. They are less like violations of physics and more like amplifiers of physics. That is why the mathematics matters, even if the script does not need to show it. General relativity gives scientists a way to describe curvature without relying on cartoons. It connects mass energy with space-time geometry. It predicts the paths of objects and light. It explains why Mercury's orbit precesses slightly differently from Newton's prediction. It predicts gravitational lensing, time dilation, black holes, and gravitational waves. That is the part that turns abstraction into reality. Black holes are not only solutions on paper. The stars near the center of the Milky Way orbit an invisible compact mass of about 4 million suns. The Event Horizon Telescope has imaged the shadow of Sagittarius A and the much larger black hole in galaxy M87. LIGO and Virgo have detected ripples from black holes merging. X-ray telescopes observe material heating near black holes in binary systems and galactic centers. A star orbiting empty darkness is data. A ring of hot plasma bent around a shadow is data. A gravitational wave chirp passing through Earth is data. A black hole forces reality to reveal that the stage itself can move, bend, and ring. This is why black holes are not only theoretical monsters. They are practical tests of whether our deepest ideas about gravity survive in the strongest conditions nature provides. When the stars near Sagittarius A follow tight orbits around a dark, compact mass, they test gravity near a supermassive black hole. When the Event Horizon Telescope images a dark shadow surrounded by a bright ring, it tests how light moves through curved space-time. When gravitational waves from two merging black holes pass through detectors on Earth, they test whether space-time itself can ripple exactly as general relativity predicts. Again and again, the universe has answered with the same strange message. Space is not passive. Time is not universal. Gravity is geometry. The universe is not a stage with actors moving across it. The stage can bend under the actors. At a black hole, the stage bends so much that part of it becomes cut off from the rest. That is the event horizon. No physical wall, no visible surface. A boundary in causality. The speed of light is not simply the speed of visible brightness. It is the speed limit for information and causality. If light cannot escape, then no signal can. The event horizon becomes a limit on what the outside universe can ever learn through ordinary communication. That is why the black hole is not only a gravitational object. It is an epistemological object too, though the word does not need to be spoken in the narration. It is a thing that changes what can be known. It places a boundary around events and says, beyond here, the outside universe cannot receive the message. That boundary is made by geometry, and geometry comes from gravity. So the journey from the cartoon black hole to the real black hole is also a journey from force to shape. Gravity is not just pulling. Space-time is curving. The event horizon is not a surface. It is a causal boundary. Escape is not about trying harder. It is about whether future paths exist at all. Once this is understood, the next part becomes even more unsettling. If the event horizon is a boundary in space-time, what would it look like to approach it? What would a distant observer see? What would the falling object experience? Would time stop? Would the crossing feel dramatic? Would light from the outside universe behave normally? The black hole has already changed gravity into geometry. Now it begins to change time itself. The event horizon is the place where that change becomes impossible to ignore. From far away, it is tempting to imagine the horizon as a visible edge, a black surface around a darker center. That is how many illustrations show it, because human eyes need boundaries. We want the black hole to have a shape we can point to, a skin we can draw, a line where the outside ends and the inside begins. But the event horizon is not a surface in the ordinary sense. It is not made of rock, gas, metal, fire, or plasma. It is a boundary in causality. Outside it, light can still escape if it is pointed in the right direction. Inside it, no direction leads back to the outside universe. That is what makes the event horizon so difficult to imagine. Nothing physical has to be sitting there. No wall has to stop you. The shape of space-time itself has removed escape from the list of possible futures. A falling object might cross it without crashing into anything, especially around a supermassive black hole. The horizon itself could be locally uneventful for something falling freely. There may be no sudden flash, no hard impact, no obvious surface. The crossing would not feel like hitting a barrier. The strange part is not what happens to the falling object at that exact boundary. The strange part is what can no longer happen afterward. No signal can return, no light beam can climb out, no message can be sent back to warn the outside universe. The event horizon is a one-way border, not because a guard stands there, but because the geometry of space-time has become one-way. That one-way nature creates one of the most famous disagreements in black hole physics. A distant observer and a falling observer do not describe the same fall in the same way. Imagine an astronaut falling toward a black hole while sending flashes of light back to a distant spacecraft. From the astronaut's own point of view, time continues normally. Their heart beats, their instruments tick. If the black hole is large enough that tidal forces near the horizon are not immediately fatal, crossing the event horizon could happen in a finite amount of their own time. But the distant observer receives a very different story. The light signals from the falling astronaut become stretched. Each signal takes longer to arrive. The light is redshifted, meaning its wavelength grows longer and its energy appears lower. The astronaut seems to slow down as they approach the horizon. Their image fades. To the outside observer, the crossing is never seen in the simple way we might expect. The astronaut appears to approach the edge, dimming and reddening, until the signal effectively disappears. This is not because the astronaut literally freezes in their own experience. It is because time and light are being distorted by gravity. That distinction matters because black holes are often described too casually as places where time stops. Time does not stop everywhere in one universal way. Time is measured along paths through space-time, and different observers can disagree about timing when gravity is strong. Near the horizon, the difference between the falling observer and the distant observer becomes extreme. The black hole does not merely bend space. It bends the relationship between observers. On Earth, this idea feels unnecessary. Two people standing a few meters apart can usually treat time as the same. Their clocks tick at almost identical rates. Their messages arrive quickly. Their shared reality feels stable. Near a black hole, shared reality becomes harder. A distant observer says the fall slows and fades near the horizon. The falling observer says they cross in finite time. Both descriptions belong to the same universe. This is one reason black holes make reality feel unstable. They reveal that time is not a single river flowing everywhere at the same speed. Time depends on motion, gravity, and the path taken through space-time. The event horizon does not simply trap matter. It exposes the fact that time itself is local. That does not mean anything can happen. Relativity is not chaos. It has rules, and those rules are precise. The unsettling part is that the rules are not the ones human intuition expects. We expect one clock for the universe. We expect one agreed sequence of what was seen. We expect that if something crosses a boundary, everyone can simply say when it happened. A black hole refuses to make that simple. The horizon divides not only space, but access to events. For the falling observer, the crossing can be part of their history. For the distant observer, information from the crossing never arrives in the ordinary way. The event is not shared by signal. It is hidden behind the boundary that no message can cross outward. That is why the word event horizon is so precise. It is a horizon for events. It also explains why the horizon can be described mathematically without being something an astronaut could touch. The boundary is global. It is defined by whether signals from a region can ever reach faraway observers. That makes it different from ordinary physical edges. A planet's surface is local. You can land on it and take a sample. An event horizon is known by the fate of paths through space-time. This is why drawings of black holes can mislead, even when they are useful. They show a dark circle because a dark circle gives the mind something to hold. But the real horizon is not the same as the black disk in an image. The dark disk is a visual effect produced by the way light moves around the black hole and fails to arrive from certain directions. The event horizon is deeper in the geometry. On Earth, the horizon is not a physical wall either. It is the line beyond which the curvature of Earth hides what is farther away. A ship sailing over the horizon has not fallen off the world. It has simply moved beyond the region from which light can reach you directly along that view. The black hole horizon is far more extreme, but the name carries a similar feeling. It is not where reality ends. It is where communication with the outside ends. The outside universe can still know the black hole by its mass, spin, and effects. It can see matter orbiting outside, measure gravitational waves from mergers, and watch stars move around it. But whatever happens inside the event horizon cannot be reported back by ordinary signals. That separation is not just dramatic, it is structural. In normal life, a locked room can still send clues. Sound can escape. Heat can leak. Light can come through cracks. A black hole horizon is not that kind of room. There is no crack in the event horizon through which a photon can sneak out. The problem is not that the door is strong. Every possible route leads inward. This is also why the event horizon is not the singularity. They are often confused, but they are different ideas. The event horizon is the boundary of no return. It can be very large. For a supermassive black hole, it can be wider than the orbit of planets. The singularity, in classical general relativity, lies deeper inside, where the equations predict an extreme end to the inward path. You do not meet the singularity at the horizon. The horizon is the point where escape becomes impossible. The horizon is not the center. It is the promise that the center cannot be avoided. That phrase is strange, but it captures the geometry. Once inside the horizon, the future direction of every possible path leads inward. The center is no longer merely a place you might choose to approach. It becomes part of what lies ahead. This is where black holes begin to feel less like objects and more like altered futures. A planet has a surface you can orbit above, land on, or leave. A star has an atmosphere and radiation and pressure. A black hole has a boundary after which the future changes shape. The deeper you think about that, the less the word hole helps. A hole sounds like an empty place in space. The event horizon is not empty. It is a limit on possible messages. It is a boundary in the causal structure of the universe. It says that some events are now cut off from outside knowledge, not by distance alone, but by the direction light itself must travel. Once crossed, escape is gone. The outside universe is gone as a destination. The falling object may still see light from outside crossing inward. It may still receive signals that enter the black hole behind it or around it, but it cannot send a reply back out. Communication becomes one way. The outside can affect the inside, but the inside cannot affect the outside by sending a normal signal outward. For the outside universe, the result is darkness. For the falling observer, the result is a future that narrows. No telescope can see through it. No detector can receive a signal sent outward from beneath it. No image can show the interior in the ordinary way. The horizon is both something we can model with extraordinary precision and something that cuts off the deepest region from direct observation. That is a rare combination in science. A boundary that can be understood from outside, but not crossed by information coming back out. It is not vague. It is not mystical. It is sharply defined in the theory. Yet it hides everything below it from the ordinary methods astronomy depends on. That combination is why black holes feel so strange. They are knowable and unknowable at the same time. We can measure their mass, infer their spin, watch matter orbit, detect waves from their mergers, and image their shadows. But the interior remains hidden behind a boundary that is not made of matter, but of the structure of causality. This is where the story moves naturally toward the next contradiction. If black holes trap light, then why are some of the brightest objects in the universe powered by black holes? The event horizon is dark. Nothing escapes from inside it. But just outside that boundary, matter can be heated, shredded, and made to glow with extraordinary power. The black hole itself is invisible, yet its surroundings can outshine entire galaxies. The darkness is real, but so is the light around it, and that is where the next part of the journey begins. The darkness is real, but so is the light around it. That is one of the strangest turns in the story of black holes. The object itself lets no light escape from inside the event horizon, yet some of the brightest environments in the universe are powered by black holes. At first, that sounds like a contradiction. If a black hole is black, how can it be connected to light so intense that it can outshine stars, galaxies, and entire regions of space? The answer is that the light does not come from inside the black hole. It comes from the matter trying not to fall in. A black hole by itself, isolated in empty space, could be nearly invisible. If no gas surrounds it, if no star passes nearby, if nothing is being torn apart or heated, then there may be very little to see. Its gravity would still be there. Its horizon would still exist. But without nearby material, the black hole would not glow in any ordinary way. The universe often gives black holes fuel, gas, dust, stars, stellar winds, material from a companion star, clouds in the center of a galaxy. When that material gets close enough, it does not usually fall straight down like water into a drain. Space is not that simple. The gas has angular momentum. It moves sideways as well as inward. It orbits, collides with itself, spreads out, and forms a rotating structure around the black hole. That structure is called an accretion disk. The disk is where darkness begins to shine. Matter in the disk can move at enormous speeds. Inner parts orbit faster than outer parts. Layers of gas rub, shear, compress, and heat. Magnetic fields twist through the plasma. Energy that was once stored in orbital motion becomes radiation. By the time gas gets close to the black hole, it can become so hot that it emits not only visible light, but ultraviolet radiation and X-rays. The black hole is not glowing. The fall toward it is glowing. That difference matters. A black hole does not break its own rule. Light still cannot escape from inside the event horizon. But outside the horizon, matter can release a tremendous amount of energy before crossing the point of no return. The black hole becomes an engine, not by shining from its interior, but by forcing nearby matter into extreme motion. This is why black holes can be both dark and bright. The center is dark. The surrounding violence is luminous. In a binary system, a black hole may orbit a normal star. If the two are close enough, gas from the star can be pulled toward the black hole. That gas forms a disk, heats up, and emits X-rays. Astronomers can detect the system not by seeing the black hole directly, but by seeing the radiation from material around it, and by measuring the motion of the companion star. Again, the black hole is known by its effects. An invisible object pulls on a visible star. A disk heats around a dark center. X-rays reveal matter moving through curved space-time. This is not science fiction. It is one of the main ways stellar mass black holes have been found. The black hole itself may be invisible, but the environment around it becomes a signal. On a much larger scale, supermassive black holes can power active galactic nuclei. These are regions at the centers of galaxies where gas falling toward the central black hole becomes extraordinarily bright. In the most extreme cases, we call them quasars. A quasar can shine across billions of light years, powered by a black hole feeding in the center of a distant galaxy. The distances matter because looking far away is also looking back in time. Some quasars are so distant that their light began traveling when the universe was much younger. That means the glow around black holes becomes a kind of record. It can tell astronomers that supermassive black holes existed early, that they found fuel, and that they were already influencing their surroundings while galaxies were still growing. This creates one of the major puzzles in modern astronomy. If a supermassive black hole contains millions or billions of solar masses, how did it grow so large so early? Did it begin from the deaths of the first massive stars? Did some black holes form from direct collapse of huge gas clouds? Did mergers help? Different ideas are still studied because quasars show us not only black holes feeding, but black holes feeding in cosmic history. A star shines through nuclear fusion. An accreting black hole shines through falling matter. That is a completely different kind of engine. The fuel is not hydrogen being fused into helium. The fuel is matter losing gravitational energy as it spirals inward. The deeper the gravitational well, the more energy can be released before the material crosses the horizon. Around a black hole, the well is extreme. The result can be an object that looks, from far away, almost impossible. A small central region brighter than the combined light of its host galaxy. Then, there are jets. In some active systems, narrow beams of particles shoot away from the region around the black hole, at speeds close to the speed of light. These jets can stretch across distances far larger than the galaxy itself. They can glow in radio waves, visible light, X-rays, and gamma rays, depending on the system and the particles involved. The important correction is this: the jets do not come from inside the event horizon. Nothing escapes from there. Jets are launched from the environment around the black hole, likely through complex interactions involving the accretion disk, magnetic fields, and the spin of the black hole. Matter and energy near the horizon can be organized by magnetic fields into narrow outflows. The exact details are still an active area of research, but the main point is clear. The black hole does not shine from within. It powers a region that can launch light and matter outward before the final boundary is crossed. This also means a black hole can affect space far beyond its own horizon. A jet may carry energy into surrounding gas, carve cavities, heat material, and change conditions across enormous distances. The horizon itself may be small compared with a galaxy, but the activity around it can matter to the galaxy as a whole. This is often called feedback. The black hole is not acting with intention, of course. It is simply part of a physical system where gas falls inward, energy comes out, and the surrounding galaxy responds. A dark central object can therefore become connected to the birth and suppression of stars around it. Even the Milky Way's central black hole, Sagittarius A, is mostly quiet compared with an active quasar. It is massive, about 4 million times the mass of the Sun, but it is not currently feeding at a dramatic rate. Around it, stars orbit. Some gas exists. Flares happen. But it is not consuming enough material to make the center of our galaxy blaze like a quasar. A supermassive black hole can be quiet. That matters because mass alone does not decide brightness. Feeding decides brightness. A black hole with little fuel can be dark. A black hole with a rich supply of gas can become one of the brightest sources in the universe. The same basic object can appear silent or brilliant, depending on what surrounds it. This changes the way we interpret the sky. When astronomers see a bright, active galaxy, they are often not seeing a star-like object in the ordinary sense. They are seeing matter under extreme gravity. They are seeing the region just outside a horizon, turning gravitational energy into radiation. The light is a warning that the black hole is feeding. Accretion disks also show how black holes turn geometry into heat. Matter orbiting farther out has a different energy from matter orbiting close in. To fall inward, gas must lose energy and angular momentum. Turbulence and magnetic processes help move angular momentum outward, allowing material to drift inward. As it does, energy is released. That also means the last visible moment is not the same as the final fate. We may see gas glow before it disappears. We do not see it cross from inside the horizon. Once it passes the boundary, the outside universe loses the message. The Event Horizon Telescope images make this concrete. The famous dark center, surrounded by a glowing ring, is not a photograph of a hard surface. It is a view of plasma, bent light, and shadow near a supermassive black hole. The black hole's gravity bends light so strongly that material behind it can contribute to what we see. The image is not a simple portrait. It is a reconstruction of light traveling through warped space-time. The ring exists because the region around the black hole is bright. The shadow exists because some light paths are lost. Again, darkness and brightness become inseparable. If there were no glowing material around the black hole, the shadow would be much harder to see. If there were no black hole, the light would not bend and vanish in the same way. The image depends on both: matter outside the horizon and a horizon that removes paths from view. That is why the phrase dark object is incomplete. Black holes are dark only at the horizon and inside it. Around them, if matter is present, the universe can become violently luminous. The darkness defines the center. The light tells us what the center is doing to everything nearby. That is the real pattern. Black holes are known by translation. An orbit translates hidden mass into motion. An accretion disk translates falling gas into light. A jet translates magnetic structure into a beam. A shadow translates missing light into an image. In every case, the black hole is not giving up its interior. It is forcing the outside universe to reveal the boundary around it. They force the universe to translate invisible structure into signals we can detect. And still, every signal comes from outside the horizon. That boundary remains. No matter how bright the disk becomes, no matter how far a jet reaches, no matter how powerful a quasar appears, the rule remains intact. The event horizon itself does not give back ordinary light. The black hole does not shine like a star. The brightness is the scream of matter before the silence, not the voice of the interior. That is what makes the next step even more personal to our intuition. If matter near a black hole can glow, orbit, heat, stretch, and fade, what would it mean to fall toward one? Not as gas in a disk, not as a distant signal, but as an object crossing into a region where time and gravity no longer behave the way human life expects. The black hole has shown how darkness creates light. Now it asks what happens when the path inward becomes your own. The black hole has shown how darkness creates light. Now it asks what happens when the path inward becomes your own. Falling toward a black hole is one of the most misunderstood ideas in space. The popular image is simple. A person drifts close, the black hole grabs them, and in one instant, they are stretched into a thin line, swallowed, and erased. The word often used for this is spaghettification, and it is real in the sense that tidal forces can stretch matter brutally near a black hole. But the real story is more careful. It depends on the black hole. It depends on the path. It depends on distance, mass, and what kind of observer is telling the story. That is already strange, because in ordinary life falling feels universal. A fall from a roof is a fall from a roof. Gravity pulls, the ground approaches, and the result is decided by height, speed, and impact. Near a black hole, falling becomes a lesson in how uneven gravity can be, and how differently time can be measured by different observers. The first danger is not the event horizon itself. The first danger is the difference in gravity between one part of your body and another. If your feet point toward a black hole, your feet are slightly closer than your head. That means the black hole pulls more strongly on your feet than on your head. Near Earth, this difference exists too, but it is tiny across the length of a human body. Near a black hole, the difference can become enormous. That difference is called a tidal force. Tidal forces are not unique to black holes. The moon raises tides on Earth because it pulls more strongly on the near side of Earth than on the far side. The same idea stretches moons around giant planets and helps heat worlds like Io and Europa. But black holes can make tidal forces extreme, especially if the black hole is small enough that the event horizon is close to the central region of intense curvature. This is where the size of the black hole matters. A stellar mass black hole, formed from a collapsed massive star, may have a horizon only tens of kilometers across. Its gravity changes very rapidly over short distances near the horizon. If a person approached such a black hole, the tidal stretching could become lethal before they crossed the event horizon. Their body would be pulled longer in the direction of the black hole and squeezed from the sides. That is spaghettification. The name sounds almost childish, but the physics is not. It describes a real stretching caused by gravitational difference. Any object, human, rock, star, or gas cloud, can be torn apart if the tidal forces become strong enough. A black hole does not need teeth. It only needs gravity to vary sharply from one side of the object to the other. Astronomers see a larger version of this in tidal disruption events. If a star passes too close to a supermassive black hole, the side of the star nearer the black hole feels a stronger pull than the far side. The star can be stretched, torn open, and pulled into long streams of gas. Some of that material may be thrown away. Some may fall back toward the black hole and heat into a bright flare. In that case, the black hole is not swallowing a star neatly. It is unmaking the star first. This matters because it replaces the cartoon with physics. The black hole does not behave like a mouth taking a bite. It behaves like a region where gravity changes so sharply across distance that an object can no longer hold itself together. Shape, identity, and structure fail before the matter itself disappears from view. Around a supermassive black hole, the story can be different. A supermassive black hole can contain millions or billions of times the mass of the Sun. its event horizon can be huge. Because the horizon is so large, the change in gravity across a human body at the horizon may be much weaker than it would be near a small black hole. In that case, an astronaut falling freely might cross the event horizon without being immediately torn apart at that boundary. There would be no solid surface, no sudden impact, no bright line to crash through. For a moment, the local experience could seem almost calm. That is one of the most unsettling facts about black holes. The most important boundary in the story may not announce itself physically to the falling observer. The event horizon is cosmic in meaning, but it may be locally quiet. From far away, however, the fall looks different. A distant observer watching the same astronaut sees the signals change. Light sent from the astronaut has to climb out of a deep gravitational field. As it escapes, it loses energy and becomes redshifted. The flashes arrive more slowly and with lower energy. The astronaut appears to slow, dim, and fade near the horizon. From the outside view, the black hole seems to stretch the fall towards silence. From the falling view, the clock still ticks. That is why saying time stops at the event horizon is too simple. For the falling observer, time does not stop at the horizon. Their own watch continues. Their thoughts continue. If the black hole is large enough, and the tidal forces are gentle enough at the horizon, they may pass through without noticing a local boundary. For the distant observer, the signals never show a clean crossing in the ordinary way. They become delayed, redshifted, and faint. The falling object becomes harder and harder to see, until it effectively disappears. Both descriptions belong to the same physical situation. That is the part our minds resist. The horizon cuts off comparison. Inside it, the falling observer's future continues inward. Outside it, the distant universe loses access. The inward path also changes what the falling observer might see. Light from the outside universe can still enter the black hole. The falling observer could, in principle, receive light from stars, galaxies, and the environment outside as they fall inward. But the view would be distorted by motion, gravity, redshift, blueshift, and the extreme bending of light paths. It would not be a simple window showing the whole future of the universe like a movie. Some light from behind the falling observer could be bent into unexpected directions. Some incoming radiation could be shifted to higher energy. The sky would not behave like a familiar dome. It would become a distorted map of paths through curved spacetime. Even before the final fate, seeing becomes complicated, because seeing depends on light, and light is following geometry that no human eye evolved to interpret. The singularity is not reached at the event horizon. That distinction matters. The horizon is the point of no return. The singularity, in the classical theory, is the place where the inward path ends. For a non-rotating black hole, the singularity is often described as lying at the center, where density and curvature become infinite in the equations. But before reaching that deeper problem, the falling object faces the unavoidable narrowing of the future. Inside the horizon, turning around no longer means escaping. Firing rockets outward no longer leads back out. Sending a signal outward does not reach the outside universe. Every future-directed path points deeper in. This is why the interior of a black hole is so difficult to imagine. The center becomes less like a location you could avoid and more like a moment you cannot prevent. The comparison is not perfect, but it helps. You cannot avoid tomorrow by turning left. Inside a black hole, you cannot avoid the inward future by choosing a different spatial direction. The geometry has made the center part of what comes next. That is more disturbing than being pulled by a force. A force can be fought if you have enough power. A future cannot be refused. That distinction is one of the most important lessons of black holes. Human danger usually announces itself as a surface, a heat, a pressure, a collision. a shock. Black hole danger can be quiet at the most meaningful boundary, because the catastrophe is not local impact. It is the loss of every path back to the universe. Real black holes can also spin, and spin adds another layer of strangeness. A rotating black hole drags space-time around with it, an effect known as frame dragging. The full details belong to a later, more technical story, but the meaning is simple enough to feel. Near a spinning black hole, even the geometry around it is being twisted by rotation. That means the path inward is not only about falling toward mass, it can involve orbit, rotation, dragged spacetime, and extreme speed. Matter in the inner accretion disk is not calmly descending. It is moving through one of the most distorted environments nature allows, where motion and geometry become difficult to separate. For the falling object, none of this restores escape. Whether the black hole is quiet or feeding, small or supermassive, rotating slowly or rapidly, the event horizon keeps the same essential meaning. Once the boundary is crossed, the outside universe is no longer a place a signal can reach. The fall also teaches us why black holes are not merely astrophysical objects, but tests of the basic structure of reality. They force us to ask what time means when observers disagree. They force us to ask what happens to information when signals cannot return. They force us to ask whether the center predicted by our equations is a real physical thing or a sign that the theory is incomplete. They force us to ask whether space-time itself has a deeper quantum structure that becomes important only under extreme conditions. That word is where the next difficulty begins. Because a singularity is not just a place where matter is dense. It is a place where the mathematics of general relativity points towards something extreme enough that the theory may be telling us its own limits. If falling into a black hole changes the meaning of escape, the singularity changes the meaning of explanation. The event horizon hides the interior from us. The singularity asks whether our equations can survive what they predict. The singularity asks whether our equations can survive what they predict. That is a very different kind of problem from the event horizon. In classical general relativity, if matter collapses far enough and no known pressure can stop it, the equations point toward a place where density and spacetime curvature become extreme without limit. The inward path does not simply lead to a hard surface, it leads to a mathematical boundary where the theory stops giving a normal physical description. This is usually called the singularity. But that word has to be treated carefully. A singularity is not something we have photographed. It is not a tiny glowing dot at the center of a black hole. It is not a confirmed physical object sitting in space, like a marble of infinite density. It is what appears when the mathematics of general relativity is followed into a regime where the theory seems to be pushed beyond its own domain. There is an important difference between a strange coordinate and a real failure of the theory. In the early history of black holes, the event horizon itself looked mathematically suspicious in some descriptions. But that problem could be removed by choosing better coordinates. The horizon was not a place where physics truly became infinite. It was partly a problem with the way the situation was being described. The singularity is not that kind of simple issue. It is not merely an awkward label that disappears when the coordinates are changed. In the classical theory, it represents something deeper, paths through space-time that cannot be extended in the usual way. The language can become technical, but the feeling is clear enough. General relativity does not simply say there is a strange center. It says that the normal description of space-time reaches an end. That is why the singularity is more serious than the horizon. The horizon hides. The singularity breaks the description. It does not mean general relativity is useless. The opposite is true. General relativity is one of the most successful theories ever created. It explains planetary orbits, gravitational lensing, time dilation, gravitational waves, and black hole behavior outside the deepest hidden regions. But success does not mean completeness. A map can be accurate across a continent and still fail at the edge of the paper. Black holes may be showing us one of the edges of the map. For a falling observer, this would not be a philosophical issue. It would be the end of the path. Inside the horizon, every future-directed route points inward. The singularity in the simplest non-rotating black hole solution is where those routes terminate. It is not somewhere you could orbit around safely once inside. It is not a central planet hidden behind darkness. It is the predicted endpoint of the fall. But the prediction itself may be incomplete. General relativity says space-time can curve, stretch, form horizons, and collapse towards singularities. Quantum theory says matter and information have rules that do not simply disappear from the universe. A black hole sits exactly where those ideas must meet. The conflict is not only philosophical. If matter collapses into an extremely small region, then its density, energy, and curvature become so extreme that quantum effects should no longer be ignorable. Yet the theory that gives us the black hole in the first place is classical. It treats space-time as smooth. Quantum physics, by contrast, teaches us that the world at small scales is not described by smooth certainty in the same way. So the central question becomes unavoidable. Is space-time truly smooth all the way down? Or is smooth space-time only an approximation, the way a calm ocean looks smooth from far away, even though it is made of molecules? A black hole does not answer that for us. It forces us to ask it. Many ideas exist: string theory, loop quantum gravity, holography, and other approaches all try, in different ways, to face the same deep problem. But none has become the final experimentally confirmed answer to what happens at the center of a real astrophysical black hole. So the honest answer is not simple. We know black holes exist. We know event horizons are part of the best description we have. We know general relativity predicts singularities under certain conditions. We do not know whether the singularity is a literal physical infinity or a sign that a deeper theory must take over. That uncertainty is not weakness. It is the frontier. The singularity is sometimes described as the place where physics breaks down. That phrase is useful if we understand it correctly. It does not mean nature becomes nonsense. Nature still does whatever nature does. The breakdown belongs to our current description. Our equations are telling us that they have been asked a question they may not be built to answer. Black holes may be doing the same thing to modern physics. They are not telling us that general relativity is wrong in the simple sense. They are telling us that general relativity may be part of a larger story. The singularity, therefore, becomes a test. Any theory of quantum gravity has to face it. It has to explain what happens when matter collapses beyond ordinary limits. It has to explain whether space-time ends, bounces, transforms, becomes quantum, or is described by something more fundamental than space-time itself. It also has to explain why the outside of the black hole behaves so well. This is part of the difficulty. We cannot replace the whole theory with something wild that ruins the successes we already have. Near and outside black holes, general relativity makes predictions that match observation beautifully. A deeper theory has to become almost indistinguishable from Einstein's theory in those regions, while still changing the story where Einstein's theory points to infinity. That is a narrow target. Too little change, and the singularity remains. Too much change, and the theory may contradict what we already observe. The challenge is that the most important region is hidden behind the event horizon. We cannot receive a signal from the singularity. We cannot send a probe in and expect data back. We cannot watch the center directly. The horizon protects the outside universe from the interior, at least in ordinary classical terms. So scientists look for indirect clues. They study gravitational waves from black hole mergers. They study black hole shadows. They study accretion disks, jets, and the motion of stars near supermassive black holes. They study the mathematics of horizons, entropy, and quantum fields. They ask, what rules must be true if black holes obey both relativity and quantum mechanics? A merger is especially useful because it shakes space-time violently and then settles into a new black hole. The final stage, called ringdown, carries information about the mass and spin of the new black hole and about whether its behavior matches general relativity. So far, the observations support Einstein's theory extremely well. That does not solve the singularity, but it tells us that any deeper theory must hide its differences carefully in the regimes we can currently observe. The shadows imaged by the Event Horizon Telescope give another kind of test. They do not show the singularity, but they test the strong gravity region outside the horizon. If the shape of the shadow or the motion of nearby light were wildly different from prediction, that would be a clue. Instead, the results so far have strengthened the idea that general relativity remains excellent outside the hidden interior. The mystery survives because the data and the theory are both strong. That is what makes the singularity so hard. That is why black holes are so powerful in theoretical physics. They are simple enough from the outside to be described by mass, spin, and charge, yet deep enough inside to threaten the foundations of our theories. Few objects in science have that combination. A star is complicated because it has layers, fusion, magnetism, plasma, convection, and nuclear reactions. A planet is complicated because it has geology, atmosphere, chemistry, and history. A black hole is complicated in another way. From outside, it can look almost too simple. Yet that simplicity hides the hardest question of all. What is space-time when space-time itself is pushed to failure? This is why the word singularity carries so much weight. It is not only a center. It is a message. It says, the theory has reached a place where the usual coordinates, densities, and curvatures no longer behave normally. The singularity is not a gap in curiosity. It is a gap in the theory. That makes it one of the most honest places in science. It shows exactly where our understanding becomes incomplete. That is the true power of the singularity in the story. It marks the point where the black hole stops being only an astrophysical object and becomes a question about the foundations of reality. The event horizon already changed escape. The singularity changes explanation. The horizon says, from here, no message returns. The singularity says, from here, our current equations no longer tell the whole story. And that is not the end of the black hole's challenge. Because if quantum physics must be included, then the horizon itself begins to change meaning too. In classical relativity, a black hole is perfectly black. Nothing comes out. It can only grow by swallowing matter and energy. But quantum theory suggests that the story is not so simple. The next step does not begin at the center. It begins near the horizon. The place that seemed like the perfect one-way boundary becomes the place where quantum effects hint that black holes may slowly lose energy, slowly lose mass, and eventually, over unimaginable timescales, evaporate. The singularity shows us where general relativity reaches its limit. Hawking radiation shows us that the horizon may not be completely silent. Hawking radiation shows us that the horizon may not be completely silent. That idea changes the black hole again. For a long time, the simplest picture was absolute. A black hole was a one-way object. Matter could fall in. Light could not come out. The event horizon marked the boundary, and once something crossed it, the outside universe could never receive a normal signal from it again. In classical general relativity, that picture is clean, powerful, and dark. But quantum physics does not let empty space be perfectly empty, in the simple way our eyes imagine. Even what we call vacuum has structure. Quantum fields still exist there. They can fluctuate. They have rules. They are not a silent nothing waiting between stars. And when quantum theory is brought near the curved space-time of a black hole horizon, the old classical picture begins to change. This is where Stephen Hawking's discovery enters the story. In the 1970s, Hawking showed that black holes should not be completely black. Because of quantum effects near the event horizon, a black hole should emit radiation. That radiation is now called Hawking radiation. The safer idea is this: when quantum fields are studied in the space-time of a black hole, distant observers should see the black hole as having a temperature and emitting a faint thermal radiation. A black hole has a temperature. That sentence is strange enough on its own. Temperature is something we associate with ordinary matter. A cup of tea, a star, a planet, a cloud of gas. A black hole seems like the opposite of that. It is a region where light cannot escape, a boundary around darkness, a place where ordinary signals are cut off. Yet Hawking's result says black holes behave like thermodynamic objects. They are not just geometry, they have temperature. For large black holes, the temperature is incredibly low. A black hole with the mass of the Sun would have a temperature far colder than the cosmic microwave background. A supermassive black hole would be colder still. This means Hawking radiation from real astrophysical black holes is far too weak to be directly detected with current instruments. It is buried under the radiation of the universe around it. That is important. We should not pretend that astronomers have directly measured Hawking radiation from a black hole in space. They have not. If a black hole emits radiation, it loses energy. If it loses energy, it loses mass. If it loses mass, its horizon shrinks. For ordinary stellar or supermassive black holes, this process would take far longer than the current age of the universe. The timescales are so enormous that they are almost impossible to feel. A large black hole is not evaporating in any dramatic way right now. It is not boiling away like water on a stove. This is why Hawking radiation feels both tiny and enormous. In the present universe, for the large black holes we know, it is effectively hidden by stronger sources of radiation around them, and by the cosmic background. But as a principle, it says that black holes are not perfect permanent vaults. They belong to time. Given enough time, the object that once seemed like the final endpoint of collapse can slowly lose what it gained. That is not a small conceptual shift. The black hole becomes part of thermodynamics, not outside it. But in principle, if no new matter falls in and the universe ages long enough, the black hole can slowly evaporate. The classical picture makes a black hole seem like a permanent trap. Quantum theory whispers that the trap itself can slowly lose mass. The event horizon remains a boundary, but the black hole is no longer frozen as an eternal thing. It becomes a physical system with entropy, temperature, and a future. Entropy is the next strange word in the story. In ordinary thermodynamics, entropy is connected to the number of microscopic ways a system can be arranged while looking the same from outside. The key idea is that entropy measures hidden information about the microscopic state of a system. Black holes have entropy, and the strangest part is where that entropy seems to live. For ordinary objects, entropy usually scales with volume. A box of gas has more possible internal arrangements if the box is larger. More space, more particles, more microscopic possibilities. But black hole entropy is proportional to the area of the event horizon, not the volume inside. Area, not volume. This is where the black hole begins to point beyond itself. If the amount of entropy is tied to the horizon area, then the boundary seems to carry a kind of accounting role. The information capacity is not behaving the way ordinary bulk matter would make us expect. It is as if gravity is telling us that boundaries may be more fundamental than they first appear. That idea will return later when the information paradox becomes unavoidable. For now, the important point is simpler. Black hole entropy says the horizon is not just a line of no return. It is also a thermodynamic surface in the equations, connected to hidden microscopic possibilities we still do not fully understand. The event horizon, which first appeared as a one-way boundary, now becomes something more. It has temperature, it has entropy. It may encode information. It is not a material war, but it behaves as if it has thermodynamic properties. Because if a black hole radiates, then we have to ask what the radiation contains. At first, Hawking radiation appears thermal. Thermal radiation is random in a certain sense. It carries temperature, but not an obvious detailed record of what made the black hole. If a black hole formed from a star, a cloud of gas, a spacecraft, a library, or anything else, the Hawking radiation seems to depend mainly on the black hole's mass, spin, and charge, not on the detailed information about what fell in. That is where the next problem begins. But before reaching it, the evaporation itself deserves attention. As a black hole loses mass, its temperature rises. This is the opposite of many ordinary objects. A small black hole is hotter than a large one. A supermassive black hole is extremely cold. A tiny black hole, if one existed, could be much hotter and radiate more strongly. This means evaporation speeds up as the black hole gets smaller. That inverse relationship is one of the reasons the idea feels upside down. Usually, adding energy makes something hotter, and a larger hot object can carry more heat. A black hole behaves differently because its temperature is tied to its horizon and mass in a way that has no everyday comparison. The bigger the black hole, the colder it is. The smaller it becomes, the hotter it gets. So, if a black hole ever reached a very small final stage, the process could become much more energetic near the end. The details of that final stage are not settled because they would require quantum gravity. Once again, the black hole carries us back to the same border. The known theory points forward, then asks for a deeper one. The end, in theory, could become more energetic. The word evaporate also needs care. A black hole does not have a surface liquid turning into vapor. The word is an analogy. It means the black hole slowly loses mass through radiation. The horizon shrinks. Energy leaves. The process is tied to quantum fields, not boiling matter. The event horizon, once imagined as the ultimate one-way boundary, becomes part of a system with a temperature. It can be described by laws that resemble the laws of heat. This creates another uncomfortable question. If black holes have entropy, what microscopic states are being counted? That question sounds technical, but it cuts directly into the deepest issue. Entropy usually means there are hidden details underneath the visible state. For a black hole, the visible state is shockingly simple: mass, spin, and charge. So where are the hidden details? Are they stored in quantum states of the horizon? Are they encoded in a deeper description of space-time? Are they not located anywhere in the ordinary sense? For a gas, we know the answer in principle. The microscopic states involve particles and their positions and motions. For a black hole, the answer is not so straightforward. What are the underlying degrees of freedom? Are they quantum states of space-time? Are they encoded on the horizon? Are they described by a deeper theory we do not yet fully understand? Black hole entropy is a clue without a complete picture. It is one of the reasons physicists suspect that space-time and information are more deeply connected than ordinary experience suggests. The area of the horizon may not just be a geometric measurement. It may be telling us something about how many possible internal or quantum configurations the black hole can represent from the outside. That is why the discovery of Hawking radiation was so important. If matter falls in, the black hole changes. Its mass may increase. Its horizon area changes. Its entropy changes. If the black hole later radiates, it loses mass. Over long enough time, the radiation carries energy away. If the black hole eventually disappears, what remains of the detailed information about everything that built it? If it was destroyed, quantum mechanics is threatened. If it escaped, Hawking radiation must carry it somehow. If it remained hidden where? After the black hole is gone. This is the black hole information paradox. It is one of the deepest problems in modern physics, and it follows naturally from the idea that black holes are not perfectly silent. The horizon that once seemed to only swallow now appears to radiate. The black hole that once seemed eternal may end. The radiation that looks thermal may have to tell a deeper story. Hawking radiation does not solve the mystery. It creates it, or more precisely, it reveals it. The event horizon asked what can escape. The singularity asked where equations fail. Hawking radiation asks what happens when a black hole has a temperature, loses mass, and may eventually disappear. And the next question is the most dangerous one for physics. What happens to the information? What happens to the information? That question sounds simple only until we understand what information means in physics. It does not only mean words written in a book, files saved on a computer, or messages sent by a radio. In physics, information is connected to the detailed state of a system, the pattern of particles, fields, energies, motions, charges, and quantum states that makes one physical situation different from another. A burned book may no longer be readable to a person, but in principle, the smoke, heat, ash, and radiation still carry traces of how the burning happened. The information has not simply become nothing, it has become scrambled into the environment. That is the normal expectation. Quantum mechanics makes this expectation even sharper. The evolution of a closed quantum system is supposed to preserve information. The details may become impossible for a human to recover in practice, but they are not supposed to be destroyed from the laws themselves. The past is not meant to vanish into absolute nothingness. That is why the paradox is not only about black holes. It is about whether the universe has one consistent way of moving from past to future. If information can truly disappear, then two different pasts could lead to the exact same final physical state. The laws would lose the ability to distinguish between histories. That would not just be strange, it would change what prediction means at the deepest level. This is why physicists use a stronger idea than memory. Human memory fails, machines break, records burn. But the underlying physical state of the universe is expected to evolve according to rules that do not simply merge many different pasts into one identical future. The information can be scrambled beyond practical recovery, but the laws should still keep track of it in principle. That phrase, "in principle," matters. It does not mean anyone could actually reconstruct a burned book from smoke and heat. It means the laws themselves are not supposed to delete the distinction between one burned book and another. Black holes threaten that principle in the most extreme way. Then, black holes enter the story. A black hole seems to take detailed things and reduce them, from the outside, to almost nothing. This reduction is called the no-hair idea in its simplest form. From outside, a settled black hole does not reveal the chemistry of the star that collapsed, the shape of the gas cloud that fed it, or the arrangement of matter that crossed the horizon. It reveals only a small set of global properties. The outside universe sees a clean result where an enormous amount of detail has vanished from view. A star falls in, a cloud of gas falls in, a spacecraft falls in, a library falls in. A black hole formed from all of them may be described from the outside by only a few properties: mass, spin, and charge. The details of what entered are no longer available to outside observers in any ordinary way. The event horizon has cut off the signals. The interior cannot send its story back. If the black hole stayed forever, the problem might feel less urgent. The information could be hidden behind the horizon, unreachable but not necessarily destroyed. It would be lost to us, but perhaps not lost to the universe. Hawking radiation changes the situation. If a black hole slowly radiates and loses mass, then the horizon shrinks. If the process continues for long enough, the black hole may eventually evaporate. Then, the vault is gone. The boundary that hid the interior disappears. Now the question becomes unavoidable. Where did the information go? If it stayed inside, but the inside is gone, that seems impossible. If it came out in Hawking radiation, then the radiation cannot be perfectly featureless thermal noise. It must somehow carry the details. If it was destroyed, then quantum mechanics is in trouble. This idea has become more favored in modern thinking. The radiation may not be perfectly information-free after all. It may look thermal in a coarse way, while still carrying hidden correlations that preserve the information. But explaining exactly how this happens, without breaking the horizon or the smoothness predicted by relativity, is extremely difficult. A useful way to imagine this is to think about a message hidden in noise. If we look at one tiny piece, it may look random. If we look at the whole pattern and understand the code, the message may be there. Hawking radiation could be similar in spirit, though the physics is far deeper than an ordinary code. The information would not come out as visible labels saying what fell in. It would have to be carried by delicate correlations across the radiation. That is why the paradox is not solved by simply saying the black hole radiates. Radiation alone is not enough. The radiation has to be the right kind of radiation. One clue comes from black hole entropy. If the entropy of a black hole is proportional to the area of its event horizon, then the horizon seems to be involved in the counting of possible states. That suggests the information content of a black hole may be connected to the boundary, not simply hidden in an ordinary volume inside. This is one of the ideas that led to the holographic principle. The holographic principle is often misunderstood. It does not mean the universe is a fake projection in the simple entertainment sense. It means that in theories of gravity, the information needed to describe a region may be related to a boundary of that region. Black holes gave the strongest clue because their entropy scales with horizon area, not volume. That one fact keeps returning like a clue left at the scene. We think of information as filling a place, but the black hole seems to count its hidden possibilities by the size of its horizon. If this is not an accident, then the boundary is not just where escape fails. It may be where the outside description of the black hole is written. That one fact keeps returning. This is why black holes are so valuable. They make hidden assumptions visible. They force physicists to state exactly which principles they are willing to keep and which may need revision. They are not only cosmic objects, they are logical stress tests. A normal laboratory cannot create an astrophysical black hole and watch it evaporate. The timescales are far too long, the radiation far too weak, and the energies far beyond human engineering. But the theory itself becomes a laboratory. By asking what must happen, physicists discover where the foundations rub against each other. One of the most important modern ideas is the Page curve. In simple terms, if a black hole evaporates without destroying information, then the radiation should first look increasingly mixed. But after a certain point, later radiation should begin to purify the earlier radiation. The curve rises, then falls. Recent theoretical work has made progress in reproducing Page curve-like behavior in certain simplified models, using ideas such as quantum extremal surfaces and islands. These are technical developments, not simple final answers for every real black hole in the sky, but they suggest that information preservation may be compatible with gravity in a deeper framework. The reason is that simplified models are not the same as the black holes we watch in the sky. Real black holes can spin, feed, merge, and sit inside messy galaxies. Their radiation is too weak to observe directly for large black holes. Their interiors are hidden. So the progress is mathematical and conceptual, more than observational. It tells us what may be possible, not a simple video of the process happening. Still, the full physical picture remains difficult. We do not yet have a simple, documentary-friendly sentence that solves the paradox honestly. It would be easy to pretend the mystery is completely solved. It would also be easy to pretend scientists have no idea at all. Neither is right. There has been real progress, especially in theoretical models, but the complete story of realistic evaporating black holes is still tied to the unfinished problem of quantum gravity. In daily life, forgetting is normal. A person forgets a name. A computer file is deleted. A paper burns. But physical forgetting is different from human forgetting. When a file is deleted, the microscopic physical state of the device and its environment still evolves according to laws. When paper burns, the atoms and photons still carry the result of the process. The information becomes scrambled, not fundamentally erased. A black hole threatens something stronger. It seems to hide the details behind a horizon, then slowly radiate in a way that might not preserve those details. If that were true, reality would not merely scramble the past, it would destroy part of it. But saving information is not free. It demands that the horizon, radiation, or space-time itself contain more structure than the classical picture first suggested. The information paradox has not made black holes less real. It has made them more important. They are no longer only the remnants of dead stars or the engines of quasars. They are tests of whether the universe preserves its own history. That is a quieter kind of mystery than a monster in space, but it is much deeper. It asks whether the rules that protect quantum information can survive in the presence of horizons, evaporation, and curved spacetime. And while this paradox is mostly theoretical, black holes also give us another kind of proof that they are real. Not through light, not through heat, not through the matter around them, but through spacetime itself. When two black holes merge, the event horizons do not send light from inside, but the spacetime outside them shakes. Energy leaves as gravitational waves. The universe carries the signal not as brightness, but as ripples in geometry. The information paradox asks what the universe remembers. Gravitational waves show that spacetime can ring. Gravitational waves show that spacetime can ring. That is not a metaphor in the usual sense. When two black holes orbit each other, they are not only moving through space, they are moving through space-time, and their motion changes the geometry around them. If the system is violent enough, those changes do not stay local. They travel outward as ripples in spacetime itself. These ripples are gravitational waves. They are not sound waves. They do not move through air. They do not need a medium like water or gas. They are stretching and squeezing of space-time, spreading outward at the speed of light, from accelerating massive objects. A black hole can be dark. A pair of black holes can still make the universe tremble. That idea brings the story into a new kind of astronomy. For most of human history, astronomy was built from light. Visible light first, then radio waves, infrared, ultraviolet, X-rays, and gamma rays. Different forms of electromagnetic radiation opened different windows on the universe, but they were still all versions of the same basic messenger: light. Black hole mergers gave us another messenger: geometry. When two black holes spiral together, they emit gravitational waves. The waves carry energy away from the orbit. As energy leaves, the black holes move closer. As they move closer, they orbit faster. As they orbit faster, the gravitational waves become stronger and higher in frequency. The signal rises like a chirp. Then, the black holes merge. For a brief moment, space-time is violently distorted. Two horizons become one. The newly formed black hole is not perfectly settled at first. It rings down, like a struck bell returning to a calm shape. But the ringing is not vibration through metal. It is the geometry of a black hole relaxing into its final form. That final form is described mainly by mass and spin. The messy violence of the merger settles into simplicity. This is one of the strangest things about black holes. Two objects can spiral together through one of the most extreme events in the universe, release enormous energy as gravitational waves, and leave behind a single black hole that soon becomes simple from the outside. The final object no longer displays all the detailed chaos of the collision. It becomes a new horizon, a new mass, a new spin. But the waves carry a record of what happened. They travel outward long after the lightless merger is over. By the time they reach Earth, gravitational waves are incredibly weak. They do not throw buildings sideways. They do not make oceans jump. They pass through the planet almost without effect. The stretching they create is far smaller than anything human senses can feel. Detecting them required instruments able to measure changes in length smaller than a tiny fraction of a proton. That is what makes the detections so extraordinary. A gravitational wave passing through Earth slightly changes the distance between freely suspended mirrors in a detector. One direction stretches while another squeezes. Then the pattern reverses. The effect is tiny, but if the detector is sensitive enough and the noise is controlled carefully enough, the signal can be found. This is what LIGO achieved. In 2015, its detectors observed gravitational waves from two merging black holes. The announcement came in 2016. It was the first direct detection of gravitational waves and the first direct observation of a binary black hole merger. A prediction from general relativity made a century earlier had become a measured signal. The universe had not only been seen, it had been felt through geometry. The scale of the measurement is almost absurd. The detectors are kilometers long, yet the change they measured was far smaller than the width of an atom. That is why there had to be more than one detector. A real gravitational wave should appear in separated instruments with the right timing and pattern, while many local disturbances would not match in the same way. Trucks, earthquakes, electrical noise, and thermal motion can all try to hide the signal. So the detection was not simply one machine noticing a shake, it was a carefully matched pattern compared against the predicted waveforms of merging black holes. That is what made it so convincing. The signal rose in frequency and strength, exactly like a pair of massive, compact objects spiraling together. Then, it ended with the ring-down of a newly formed black hole. In a fraction of a second, the data carried the story of two black holes becoming one. This makes gravitational wave astronomy a new sense. A telescope catches light. A gravitational wave detector listens to spacetime. The signal has three main parts: in-spiral, merger, and ring-down. During in-spiral, the two black holes orbit each other, losing energy to gravitational waves. Their orbit shrinks, and the frequency rises. During merger, the horizons combine into one. During ring-down, the final black hole settles. Each part carries information. This is why gravitational waves are not just detections, they are tests. This is the pattern again. The outside is knowable, the inside remains hidden. Gravitational waves come from the spacetime outside and around the horizons, as the black holes orbit and merge. They do not bring us a message from the singularity. They do not reveal what happens behind the event horizon, but they do reveal that horizons can move, merge, and settle in ways that leave measurable traces across the universe. This is one of the most elegant parts of general relativity. Gravity is not only something that shapes motion, gravity itself can carry energy through waves. Space-time is not frozen background. It can ripple, propagate, and settle. Black holes make that undeniable. That is a major difference between Newton's picture and Einstein's. In the older intuition, gravity feels like an invisible influence between masses. In relativity, Changes in gravity do not update the entire universe instantly. Disturbances in the gravitational field travel outward at the speed of light. If a massive system changes violently, space-time carries the news away as a wave. This makes a merger feel less like two objects colliding inside a fixed universe and more like the universe itself participating in the event. The black holes move. The geometry responds. The waves leave. This is one reason the ninth step in the journey matters. We began with black holes as invisible objects. Then, we saw their shadows and their glowing disks. Then we entered the questions of horizons, singularities, radiation, and information. Now, gravitational waves show that even when black holes are dark, they are not silent to space-time. A black hole merger is almost pure gravity made observable. No ordinary surface. No material collision like two rocks smashing together. No explosion in air. No sound in space. Just the geometry of the universe changing shape and sending that change outward. We no longer only ask what shines. We ask what moves space-time. That question opens a dark part of the universe that light alone could not map. Some black holes may never feed brightly. Some binaries may merge with little surrounding gas. Some events may be hidden in places where electromagnetic telescopes see nothing unusual. Gravitational waves do not need the event to be luminous. They need the mass to move in the right way. This is why the word observatory has changed. An observatory can now be a laser interferometer on Earth, measuring distance changes so tiny that the human mind almost cannot hold them. It can be an instrument built not to collect photons, but to notice the breathing of space-time. The universe is not only visible, it is measurable in geometry. That shift is especially important for black holes, because they are defined by the failure of light to escape from inside the horizon. Electromagnetic astronomy sees their surroundings. Gravitational wave astronomy sees their motion and merger. Neither sees the interior directly, but together they give a much richer picture. The shadow shows where light fails. The disk shows where matter glows. The wave shows where space-time rings. Each messenger tells part of the story. None tells all of it. And gravitational waves make the reality of black holes harder to dismiss than ever. They show that black holes are not merely inferred from missing light. They are dynamical actors whose motion shakes the geometry of the universe. The signal can be weak when it reaches us, but the event that made it is enormous. This is one of the most beautiful reversals in the entire story. Black holes began as objects defined by what cannot escape, but when they merge, they send one of the clearest messages in modern astronomy. Not light from inside, not matter from the horizon, a wave in space-time itself. That is why gravitational waves belong near the end of this journey. They are not a side topic. They are the proof that black holes are not only theoretical traps or distant shadows. They are moving pieces of space-time that can interact, merge, and leave behind a signal written into the fabric of the universe. They show that the same theory that gives us horizons also gives us waves. The same geometry that traps light can ring. The journey began with the simplest false image, a dark object sucking in everything around it. It has become something far deeper, a region where space-time curves into a horizon, where time depends on the path taken, where matter can glow before silence, where equations point towards singularities, where quantum effects suggest evaporation, where information becomes a paradox, and where merging horizons send waves across the cosmos. The final step is to pull these pieces together, because black holes do not break our understanding of reality by being impossible. They break it by being real. They are real enough to orbit, real enough to image, real enough to merge, real enough to ring the universe. And because they are real, the questions they raise cannot be dismissed as imagination. They may be pointing toward the deeper theory that waits beyond the edge of what we currently know. They may be pointing toward the deeper theory that waits beyond the edge of what we currently know. That is where the final meaning of black holes begins. Not as monsters, not as holes in the simple sense, not as cosmic vacuum cleaners waiting to swallow everything, but as places where the universe gathers its deepest questions into one physical object. Around a black hole, the ideas that feel separate in ordinary life are forced together. Gravity becomes geometry. Geometry creates a horizon. The horizon changes what can be known. Quantum theory gives the horizon a temperature. Thermodynamics gives it entropy. Information theory asks what the black hole remembers. Gravitational waves show that the space-time around black holes can ring. One object touches almost every foundation. That is why black holes break our understanding of reality. Not because reality becomes nonsense, and not because physics has failed in some dramatic, careless way. They break our understanding because they reveal that our first picture of reality was always too small. Human beings evolved in weak gravity. We live on a surface. We move slowly compared with light. We experience time as steady. We see objects because light bounces from them into our eyes. We separate space from time because daily life allows us to do so. Black holes live outside that world. They are not built for human intuition. They are built from the rules of the universe pushed into a regime our senses never had to understand. A black hole is what happens when mass, gravity, light, time, information, and quantum theory meet under extreme conditions. That is why every simple description eventually breaks. If we say a black hole is a dead star, the description fails, because supermassive black holes are far more than ordinary stellar remnants. If we say it is a hole in space, the description fails, because it is not empty in the simple sense. If we say it is a place where nothing escapes, the description helps, but then Hawking radiation complicates the story. If we say it is completely dark, the accretion disk can become brighter than galaxies. If we say physics ends there, general relativity continues to work beautifully outside the horizon. If we say physics is complete there, the singularity and information paradox tell us something is missing. Every sentence about black holes is useful only for a while. Then, the next layer changes it. That does not make black holes impossible to understand. It makes them difficult in the best scientific sense. They are not vague mysteries. They are precise mysteries. We can calculate parts of them. We can observe their effects. We can measure their masses. We can image their shadows. We can detect waves from their mergers. We can test predictions from general relativity with extraordinary detail. And still, the deepest questions remain. The event horizon is the first great lesson. It tells us that a boundary does not have to be made of matter. A boundary can be made of causality. It can be a line beyond which events cannot send messages back to the outside universe. No wall, no surface, no metal shell. Just the structure of space-time deciding which paths are possible. That alone changes what reality means. In ordinary life, if something exists, we imagine it can in principle be seen, touched, signaled, or reported. The event horizon says there can be regions of the universe whose events are physically cut off from the rest of us. Not because they are too far away, not because our telescopes are too weak, because no outward signal can leave. The universe can contain hidden chapters. The singularity is the second lesson. It tells us that even our best classical theory of gravity can point toward a place where the language of space-time becomes incomplete. Again, this does not mean nature becomes nonsense. Nature does whatever the deeper laws say. The problem is that our current description does not yet tell us the full answer. That is a different kind of darkness. The event horizon is observational darkness. The singularity is theoretical darkness. One hides events from outside observers. The other hides the final explanation from our current equations. Then, Hawking radiation adds the third lesson. The horizon may not be completely silent. A black hole can have a temperature, it can have entropy, it can slowly lose mass through quantum effects. It may not be an eternal prison after all. The object that looked like the final endpoint of collapse becomes part of a process. If a black hole can evaporate, then hiding information forever behind the horizon is no longer enough. The black hole may not remain as a vault. The radiation must either carry the information in subtle correlations, or information must be destroyed, or some deeper idea must change the way we understand the situation. This is where black holes become more than astronomy. They become arguments about reality itself. And then, gravitational waves give the fifth lesson. Black holes are not just hidden. They move. They merge. They shake space-time. A pair of black holes can collide in darkness and still send a signal across the universe, not as light, but as a ripple in geometry. The event horizon traps light from inside, but the space-time outside the moving black holes can ring. That is why they may be doorways to deeper physics. Not doorways in the science fiction sense, not portals a spacecraft can safely use. Doorways in the intellectual sense. They mark the entrance to a problem we cannot solve with one theory alone. Black holes are among the strongest clues that such a description is needed. They do this without giving us the answer too quickly. The horizon blocks the direct view. The singularity sits beyond direct observation. Hawking radiation is too faint to measure from large real black holes today. The information paradox is sharpened by mathematics more than by a simple image. Every clue is powerful, but none is the full solution by itself. They do not whisper that clue. They shout it quietly. A horizon with entropy, a singularity in the equations, radiation from a black object, a paradox about information, a space-time wave from a dark merger. Each clue points toward a reality deeper than the one our instincts expect. Black holes show that reality is lawful even when it is unfamiliar. The laws are not gone. They are being pushed to their boundary. That is why the most honest feeling is not panic, it is awe. At the center of the Milky Way, stars orbit an invisible mass millions of times heavier than the Sun. In distant galaxies, supermassive black holes feed and power quasars. In radio images, we see shadows surrounded by bent light. In gravitational wave detectors, we measure the final moments of black hole pairs. In theory, we follow the consequences of horizons until they lead us to entropy, evaporation, and information. What is space-time? What is time? What is information? What does it mean for something to be hidden? What does it mean for the universe to remember? These are not questions we would naturally ask while standing under the night sky. The stars look calm. The moon looks simple. The sky feels like a ceiling above us. But far beyond the familiar view, black holes remind us that the universe is not built around human comfort. It is deeper, older, stranger, more precise, and less intuitive than our first picture. That is why the title matters. Black holes break our understanding of reality, because our understanding began in the wrong scale. It began with solid ground, normal clocks, gentle gravity, and light that usually travels in straight lines. Black holes live where those assumptions stop being enough. They do not break reality. They break the small version of reality we carried in our minds. Then they invite us to build a larger one. This is why black holes may be among the most important objects ever studied. Not because they are the most dangerous things in the universe, though they can be destructive. Not because they are the strangest looking, because often they cannot be seen directly at all, but because they sit at the crossing point between what we know and what we still need to know. That crossing point is rare. Many objects teach us one area of physics beautifully. Stars teach fusion and plasma. Galaxies teach structure and gravity on vast scales. Atoms teach quantum behavior. Black holes pull those separate lessons together. They are places where the very large and the very small stop being separate subjects. They are the edge of a map that is still being drawn. And the map is not blank. That is the important part. We have landmarks now. Shadows, orbits, accretion disks, X-rays, jets, gravitational waves, equations, entropy, and paradoxes. The unknown is surrounded by real structure. That makes the search more serious, not less. And the edge is real. Somewhere right now, a black hole is quietly orbiting with a companion star. Somewhere else, gas is heating in an accretion disk before vanishing from view. Somewhere in the deep past, a quasar is sending light across billions of years. Somewhere, two black holes may be spiraling toward each other, slowly losing energy until the final moment arrives and space-time rings again. And somewhere in our equations, the same questions wait. The journey began with darkness. It ends with a deeper kind of light. Not light escaping from inside the black hole, but light in the human sense. Understanding. A clearer view of what we know, what we do not know, and where the next theory may have to begin. Thank you for watching this journey into black holes and the edge of modern physics. If you enjoyed it, leave a like, subscribe for more calm space documentaries, and write in the comments which part of black holes feels the hardest to understand. Time, the event horizon, the singularity, Hawking radiation, information, or gravitational waves. Wherever you are watching from, and whatever time it is there right now, remember that time itself is not as simple as it feels from Earth. Good night.